Let's look at the variance and the standard deviation. All right, let's talk a little bit about the standard deviation before we look at the math. Let's say that I have a number line and I have stacked up my data here and I have a nice bell curve, so I have a mean right here of some value. And what I really want to measure with the standard deviation is how far from that point, from the mean, do the data extend in both directions. So the standard deviation assumes that we have a symmetrical data set. The reason it's important is I could have a data set with the same mean that has much less dispersion, right? It could look like this. That's the same mean, but it has much less dispersion. Or I could have one that is much greater, right? So that data goes from all the way from here to here. And these data just go from here to here, and then from here to here, right? Sorry, let's make that black. From there to there. So we have different amounts of dispersion. And what we're trying to look for is a measure that will take into account, or that will measure how far away from the mean a typical data set or a typical value is in the data. So let's look at a simple example. And we'll keep this one short. Let's say we have 1, 3, 4, 5, 5, and 6. Okay. And if we look at the mean of these data, that adds up to 24 divided by 6. So the mean of these data is equal to 4. So if I take each of these data, what I'm trying to get at is how far away are they from the mean, right? That's the idea over here. How far away are they typically from the mean? So let's just measure how far away they each are from the mean. We have a 1, 3, 4, 5, 5, and 6, and we'll just subtract the mean from each of these. And so in this case, we have -3, -2, 0, 1, 1, and 2. Now the problem is if I add these up, oh sorry, this is a -1, isn't it? If I add these up, they are going to cancel each other out, and the answer will be 0, right? -3 and -1 is -4. 2 plus 1 plus 1 is +4. They're canceling each other out, and we have zeros. So we need to get rid of the sign. And the way we're going to do that is by squaring them. And I'm just going to change colors here because I can. But -3 squared is 9. 1 squared is 1, 0, 1, 1, and 4. Okay, so now I have values that I can add up. 10, that becomes 16. And so now I have some measure of how far the distance really is. I can divide this by n, which my n over here we didn't talk about, but n was equal to 6. But instead of dividing that by 6, we're going to divide it by 5. We're going to divide it by n minus 1. And we do that to make the standard deviation a little bit bigger. As a statistician, I'm worried about making mistakes. And the biggest mistake I can make here is claim that I have a small dispersion when actually it was quite large. So let's look at what we've done here so far. We've taken each individual value for x, and we've subtracted from it the mean, and then we squared it, and then we summed it up, okay? And then I kind of awkwardly there explained that we're going to divide this by n minus 1 instead of by n to give us a little bit of cushion. Okay, this value is called the variance, which we denote statistically as s squared. The problem with this value, and the reason we don't use it more often, is because we've squared it, right? Well, we can't get away from it. We have to square it. But let's say that we were looking at the amount of money that the average geography graduate made after school, right? We would say that their mean was a certain number of dollars. Let's just to make it easy, let's say $50,000. And then their standard deviation, or in this case their variance, we would be reporting in dollars squared, which is not meaningful at all. So the standard deviation, which we use much more often, is the same thing as the variance, each observation minus their mean squared and then summed and divided by n minus 1, but then we take the square root. And so the standard deviation is equal to s. And that is, we use that much, much more often. All right, calculating the standard deviation and the variance in R is easy. As always, you're getting used to me saying that, right? So the data set that we were looking at were the numbers 1, 3, 4, 5, 5, and 6. We could write out the full equation for the standard deviation, which I think I will do just to show you so that you can become a little bit more familiar with using R. But we're going to take each observation minus the mean of those observations, right? Then we're going to square it, and then we're going to sum it up. All right, so that's our numerator. And then we're going to divide that by n, which is equal to the length of x minus 1. So that gives me the variance. If I then take the square root of all of that, that gives me the standard deviation. Right, so there is our standard deviation. Zoom in a little bit better so you can see that. The other way to do it, of course, would just be to do standard deviation. Quite a bit simpler. The variance is equal to the variance of x, which means, I guess, that you could also technically say the square root of the variance of x. This would also give you the standard deviation, right? So here we have 3 different ways of calculating the standard deviation, and here we have the variance, okay? So I will highlight all of these and send them over hitting Control Enter, Command Enter. If you're using a Windows machine, it is Control R, and we'll take a look at the results here. So here we've input the data. Here is our equation for calculating the standard deviation, where we're building it step by step. We get the same result if we just use the standard deviation function, and we get the same result if we take the square root of the variance, right? And here our variance for these data was 3.2. So once again, we have lots of ways of calculating standard deviation variance. Obviously, these straightforward methods are probably your best bet.